Imagine for a moment you're tasked with building the logistics backend for an e-commerce giant. I mean, we're talking millions of shipments, integrating with dozens of different carriers, ensuring every single financial transaction is absolutely perfect.
Mm-hmm.
And all of this, mind you, while navigating a market as vast and complex as India. It's a monumental undertaking, right?
Absolutely huge.
And today, we are pulling back the curtain on a company that has, well, truly mastered this challenge. Shiprocket. Welcome to the deep dive. This is where we take a whole stack of information articles, research our own notes, and, break it all down into the most important nuggets of knowledge for you. We cut through the noise to get right to the core. Today, we're embarking on a really in-depth exploration of Shiprocket's entire architecture and its operational flow. Our mission here is to demystify what it takes to build a truly world-class logistics platform.
Yeah, and this isn't just theory, right?
No, exactly. What we're about to uncover is a production-validated system. We've carefully, let's say, reverse engineered it from its official API documentation and observable operational patterns.
Based on what we can actually see.
Precisely. We'll unravel its core components, dive deep into the design decisions, understand the critical why behind specific technology choices, and explore the crucial trade-offs made to build such a robust and scalable system. Our goal is to provide you with a complete source of truth, making even the most complex technical details clear and understandable, no matter your level of expertise. Think of this as your comprehensive audiobook on Shiprocket's engineering mastery. And what's particularly striking as we've dug into the material is Shiprocket's core philosophy. It really seems grounded in observable reality.
That's a perfect way to put it. It's a key takeaway. This architecture isn't about, theoretical ideals you might read in a textbook. It's about what actually works in production day in, day out. It meticulously avoids abstract patterns that don't align with Shiprocket's real-world implementation. The focus is always on how the system practically operates, based on verifiable API behavior. And this pragmatic approach, it informs every single design decision, from their choice of, say, concurrency models right through to their integration patterns.
Okay, and that pragmatism extends directly to their business focus, too, which seems to be logistics first, not e-commerce all in one. That's a really crucial distinction, isn't it?
Absolutely. Shiprocket has clearly chosen to specialize. They aim to be world-class at shipping, managing returns, and those deep carrier integrations. What they explicitly don't do is process payments for the end customer, the person buying the goods. That's the domain of the seller's own e-commerce platform, like Shopify or Magento.
Right.
However, and this is critical, they do manage the financial relationship between the sellers and the carriers. This specific focus allows them to build incredibly robust systems for their particular niche.
So they're not trying to boil the ocean, basically. They're focused. And within that focus, it seems their core operations are designed for absolute certainty.
Precisely. Core operations like creating an order are synchronous and atomic by default. What that means is, when you send a request to create an order, you get an immediate response back, success or failure. It's designed as a single, indivisible transaction.
Okay, now waiting around for something to happen later.
Exactly. And for resilience, they use a hybrid integration pattern with e-commerce platforms. So they'll register webhooks for real-time updates from platforms like Shopify, which is great for speed, but they also actively pull for data from others like Amazon and Flipkart, which might not offer the same webhook capabilities. This redundancy ensures no data is missed, even if, say, a webhook call fails.
That makes a lot of sense for data integrity. Now, given they operate primarily in India, I imagine India-first compliance and operations plays a massive role in everything they do.
Oh, it's fundamental. GST compliance, that's India's goods and services tax and data localization, making sure all sensitive data stays within the Mumbai AWS region, App South 1. These are primary concerns woven right into the fabric of their architecture.
So that impacts everything from database choices to API designs.
Everything. Data storage, specific API validations, reporting. What's also interesting is that while many carrier status updates are fully automated, things like picked up or in transit, some critical steps like the actual pickup approval often involve a human in the loop.
Ah, okay. So a real person has to click approve.
Often, yes. This reflects the practical realities of logistics, especially in a diverse market like India, where sometimes a human check is just more reliable than pure automation for certain critical points.
That blend of automation and human oversight for critical junctures sounds very sensible, very pragmatic. And for developers interacting with their system, what about their API structure reality? Is it consistent?
Very much so. For anyone looking at their public APIs, you'll immediately notice a consistent pattern. All public endpoints follow the V1 external resource path structure.
Right.
It's clear, it's versioned V1, and it's explicitly marked as externally facing. And for authentication, they use standard JWT authentication, JSON Web Tokens. These are self-contained tokens proving identity.
And how long are those tokens valid for?
They have a relatively long validity, 240 hours, which is 10 days. This actually simplifies things quite a bit for the client-side management, reducing the need for constant token refreshes.
Okay. And as we delve deeper, you mentioned a balance reservation pattern that keeps coming up as a critical theme.
Yeah.
Could you elaborate on what that is and why it's so important for them?
Certainly. This pattern is absolutely crucial for their financial integrity. Specifically, it's designed to prevent race conditions in financial operations between the sellers and the carriers.
Okay. Race conditions.
Mm-hmm.
Like trying to spend the same money twice.
Exactly. Or spending money you don't quite have yet because another operation hasn't fully completed. Think of it like a temporary hold on funds. When a seller initiates creating an order, an estimated amount for the shipping cost is reserved from their Shiprocket account balance. It's not actually debited yet, but it's set aside. This prevents the seller from inadvertently overspending that balance on, say, another order before the shipping label is actually generated and paid for.
Got it. So it's like putting a temporary lock on the estimated funds.
Precisely. If the order gets canceled before the label is generated, that reservation is simply released. But if and when the label is generated, the system knows those funds are guaranteed to be there, and the reservation is converted into an actual charge. It provides an atomic financial operation for that critical step.
That makes perfect sense for a prepaid shipping credit model. So what does all this context mean for how we've approached this deep dive for you, our listener? How are we structuring this analysis?
Well, it means our analysis distinguishes very clearly between what we call verified facts. These are things directly observable from Shiprocket's official API documentation and its actual behavior in the wild.
Right, stuff we know for sure.
Exactly. Then there are plausible inferences. These are logical extensions and, frankly, best practices that a system operating at this kind of scale must employ, even if they aren't explicitly documented. Things like robust rate limiting or idempotency.
Makes sense. You wouldn't build something this big without them.
Right. And finally, we might touch on recommended enhancements, just suggestions for future improvements based on industry best practices. But the core approach prioritizes technical credibility above all else. We're cutting through any marketing claims to give you a true engineering-focused understanding of how this thing is built.
Excellent. With that foundational understanding locked in, let's now start our journey through Shiprocket's architecture, beginning right at the very front door. The API gateway. This isn't just some simple entry point, is it? It's the secure, highly available, and observable first point of contact for every single request that enters Shiprocket's ecosystem.
Exactly. It's mission critical. From our observations, its primary API validated functions are pretty multifaceted. First, it terminates TLS for all incoming REST API requests. That's the encryption layer, transport layer security, that keeps internet communications secure.
So it handles the HTTPS part.
Correct. So when you send, say, a POST V1 external order SCRI ad hoc request, the API gateway is the first component to decrypt it. Crucially, it then validates authorization. It inspects that bearer token header using the JWT token we talked about for stateless authentication. Stateless meaning it doesn't need to store session info locally.
Yep.
And of course, it handles standard HTTP methods like GET-T, POST-TASK, POT, routing them appropriately to the correct internal service.
So it's definitely not just a simple pass-through. It's an active gatekeeper doing real work. And for a system handling potentially millions of requests daily, I'm sure it incorporates some truly advanced features, what we're calling AFANG-grade enhancements. What are some of the inferred capabilities here that you'd expect?
Well, a critical one, almost certainly, is idempotency enforcement. This is a huge best practice for production reliability, especially with APIs.
Right, preventing accidental duplicates.
Exactly. Imagine a client sends a POST request to create an order, but maybe due to a network glitch, they don't get a response back quickly, so they retry. Without idempotency, that could easily create two identical orders, causing chaos.
Yeah, it's bad.
So the API gateway likely prevents this by using an idempotency key header. This is a unique identifier sent by the client with the request. The gateway remembers this key for a short period. If it sees the same key again for the same type of request, it just returns the original successful response without reprocessing the request internally. This prevents duplicate resource creation, and it happens server-side, meaning the client doesn't need complex retry logic.
That's a massive operational benefit, takes the burden off the client.
Yeah.
What else does it do to protect the system from being overwhelmed?
It almost certainly employs adaptive rate limiting, probably using a sophisticated token bucket algorithm backed by a fast cache like Redis.
A token bucket. How does that work conceptually?
Think of it like a bucket that holds tokens. Each incoming request needs to take a token from the bucket to proceed. Tokens are added back to the bucket at a steady rate. If the bucket is empty, the request has to wait or gets rejected.
Okay, so it smooths out bursts.
Exactly, and this is likely applied on a per-seller basis, so no single seller can swamp the system. It ensures fair usage, especially during peak loads like India's big festive sales seasons. Internally, for security between services adopting a zero-trust security model, it probably enforces strict MTLS, or mutual TLS.
Mutual TLS. So not just the client verifying the server, but the server verifying the client too.
Precisely. Both sides verify each other's digital certificates for all outgoing gRPC calls to internal services. This is likely combined with something like SPACE identity, which is an open standard providing cryptographically verifiable identities for software services. It ensures that only authenticated and authorized internal services can talk to each other.
Wow, okay. So it's not just checking who's at the front door, it's also making sure all the internal conversations are completely secure and verifiable. That's serious. And for understanding what's actually happening within this complex system, how does it help with observability?
For trace propagation, it's invaluable. The gateway likely injects an X-request ID header into every single incoming request. This unique ID then gets passed along to every subsequent service call made as part of handling that initial request. This creates a distributed trace.
So you can follow a single request journey through all the microservices.
Exactly. Tools like Jaeger or Zipkin can then visualize this trace, giving engineers end-to-end visibility into how a request flows through the entire system. It's crucial for debugging and finding bottlenecks.
Makes sense.
It also acts as the first line of defense with a web application firewall, WAD. This is a standard security solution that protects against common web attacks like SQL injection, cross-site scripting, XSS, and Layer 7 DDoS attacks. Furthermore, it strictly enforces API version validation, requiring that v1 prefix and rejecting unversioned or maybe deprecated endpoints, which helps maintain API stability over time.
Right, keeps things clean.
And naturally, for handling high traffic volumes, it manages concurrency through techniques like connection pooling and request queuing, ensuring the system remains stable and responsive even under heavy load.
That's a huge amount of responsibility for one component. So for scaling and performance, how is this critical piece designed to actually cope with potentially massive scale?
It's definitely designed for horizontal scaling. That means you can just add more instances of the gateway to handle more load. This is typically managed by something like Kubernetes autoscaling, which automatically adds or removes instances based on traffic.
Okay, scales out.
Yeah. It likely targets handling up to maybe 1,000 requests per second per instance. If you do the math, that's roughly 120 million requests a day, just for context. Error handling is robust. You get a 401 status code for invalid tokens, a 429 for hitting rate limits. And there are optimizations like caching frequently accessed data, maybe those pin code serviceability checks, and compressing JSON responses using gzip, which is crucial for network efficiency, especially in a market like India with varying internet speeds.
A truly impressive and hardworking front door. But once a request gets through that gateway, how does Shiprocket know who that request is actually coming from? That brings us logically to the auth service. This seems to operate as a kind of global plane, focusing strictly on machine-to-machine authentication, right? Not user logins.
That's exactly right. Its primary API-validated function is the POST v1 external auth login endpoint. This is where a seller system, not a human user in a browser, authenticates using an email and password pair.
Right, for their back-end integrations.
Precisely. In return, it gets that JWT token we mentioned earlier, the one valid for 10 days. The token structure follows the standard JWT format, meaning it's self-contained and cryptographically signed, proving its authenticity. And naturally, a valid token obtained from this service is required to access pretty much all other protected API endpoints. Internally, it also must have mechanisms for token revocation, if a token is suspected of being compromised.
Okay. For a service so absolutely critical to security, what are some of the FEN-grade enhancements that likely go on behind the scenes? What makes it truly robust?
High-speed token validation is paramount. You can't afford to decrypt and verify the signature of every JWT from scratch For every single API request hitting the gateway, that would be way too slow.
Yeah, that'd kill performance.
Right. So active valid tokens are almost certainly cached in a high-speed in-memory store like Redis. This allows the API gateway to perform sub-millisecond validation checks just by looking up the token ID in the cache, ensuring performance isn't sacrificed for security.
Smart caching.
And for the ultimate security of the signing process itself, all cryptographic operations like actually signing the JWTs and the storage of the master secret keys probably occur within a hardware security module, or HSM. Think AWS Cloud HSM or similar.
HSM, that's dedicated hardware, right?
Exactly. An HSM is a physical device specifically designed to protect cryptographic keys. It ensures the keys are generated, stored, and used entirely within the secure hardware boundary and are never exposed in software, memory, or logs. It's top-tier security practice.
So the most sensitive keys are literally locked away in specialized hardware. That's impressive. What about accountability and auditability?
Immutable audit logs are absolutely critical here. Every significant token-related event, think generation, validation attempts, successful logins, revocations, is logged to an immutable storage system.
Immutable meaning can't be changed.
Correct. Once written, these logs cannot be altered or deleted. Think of using something like Amazon S3 with object lock enabled, combined with AWS CloudTrail for API activity logging. This provides a verifiable, tamper-proof trail for security audits and compliance requirements, often needing retention for many years.
Got it.
There's also likely a token rotation mechanism in place. Even though the tokens last 10 days, the system probably automatically prompts seller systems to refresh their tokens periodically, maybe before they expire, ensuring uninterrupted service and proactively reducing the risk associated with long-lived tokens.
Makes sense. And for handling concurrency, like if two systems try to log in or revoke the same token at once.
Right. For concurrency control, especially during sensitive operations like token revocation, Redis is likely used again, this time for distributed locking. If multiple requests try to revoke the same token simultaneously across different service instances, this locking mechanism ensures only one succeeds, preventing race conditions and ensuring the revocation is atomic and consistent everywhere.
Sounds like a truly robust and well-thought-out security system. For scaling and performance on this auth service, what does it need to handle?
Well, this service needs to be designed to support potentially thousands of concurrent logins, especially if many seller systems re-authenticate around the same time. Token generation itself should be very fast, typically completing in well under 100 milliseconds. Error handling is pretty straightforward. A 401 unauthorized response for invalid credentials. Performance is optimized using strong, computationally intensive hashing algorithms like bcrypt for storing password hashes securely. Never store plain passwords. And a standard like HS25TX is likely used for signing the JWTs. Critically, it must include brute force protection features.
Like locking accounts after too many failed attempts.
Exactly. Account lockouts, maybe CAPI TCHs after a few failures, and adaptive throttling slowing down login attempts from a specific IP if it fails too often. Redis's setNX command, which means set if not exists, is often used here for simple distributed locking to prevent multiple simultaneous login attempts on the same account from different servers.
Okay, so once a seller is properly authenticated, they usually need to connect their actual e-commerce store, like their Shopify or WooCommerce site. That brings us to the channel management service. This sounds like it handles the administrative heavy lifting for integrating with all those different external platforms.
That's precisely its role. Its primary API-validated functions include GET v1 external channels. This lists all the available integrations Shiprocket supports, Shopify, WooCommerce, Magento, Amazon Seller Central, Flipkart Seller Hub, and so on.
Just listing what's possible.
Right. And then there's POST v1 external channels connect. This endpoint handles the entire OAuth 2.0 flow for connecting a platform. OAuth 2.0 is the industry standard for delegated authorization. It allows Shiprocket to securely access a seller's data on another platform without the seller ever having to give Shiprocket their actual login credentials for that platform.
Oh, the familiar allow Shiprocket to access your data prompt.
Exactly that flow. This service manages that whole process and securely stores the resulting platform-specific API credentials, the tokens and keys needed for Shiprocket to talk to that platform later.
So it's not just about listing the channels, it's about managing the entire life cycle of those connections. What sort of advanced features might it employ to make this reliable?
A key FANG grade enhancement here would be secure credential storage. All those external API keys and tokens obtained via oath must be encrypted at rest, probably using strong AES encryption, and stored securely in a dedicated secrets management system. Think HashiCorp Vault or AWS Secrets Manager.
Keeps them out of the main database and code.
Absolutely. Keeps them highly protected. There's also likely active connection health monitoring. This service doesn't just set up the connection and forget it. It probably actively probes these connected channels periodically, maybe tries a simple API call to ensure that the authentication tokens are still valid and the integration is generally healthy.
Proactive checks.
Yes. If a token expires, or maybe the seller revokes access on the platform side, this service can detect that and proactively alert the seller that they need to re-authenticate, preventing unexpected service interruptions down the line.
That kind of proactive alerting is always better than reactive firefighting when orders stop syncing.
Indeed. For platforms that support it, like Shopify, this service also handles webhook registration. It tells the e-commerce platform, hey, whenever a new order comes in, send a notification to the Shiprocket URL. This enables real-time updates. It also seems to play a role in multi-platform consistency, potentially acting as a sort of reconciliation engine for inventory views across different connected platforms, although the heavy lifting for sync happens elsewhere. Our plausible inference here regarding how it might contribute to inventory consistency views is using a timestamp-based last write wins, LWW, approach with millisecond precision.
Okay, last write wins, so the most recent update takes precedence.
Generally, yes. While more complex algorithms like vector clocks can track the causal history of updates across platforms, which we'll discuss later for the actual sync service, for just providing a unified view or basic reconciliation in the channel management service itself, LWW is often simpler to implement and sufficient. It's a practical trade-off between complexity and the specific goal here.
That makes sense. Balancing complexity with the immediate need. What kind of capacity estimates are we looking at for a service like this, managing all these connections?
Well, this service needs to handle the configuration for potentially over 500,000 seller accounts. And collectively, these sellers might have upwards of 1.2 million individual platform connections configured.
Wow, that's a lot of integrations.
It is. It likely relies on a substantial database, maybe around 8 terabytes, primarily to store potentially 7 years of audit logs related to these connections for compliance and history. And it needs to be designed to handle a peak load of perhaps 15,000 requests per second for channel-related operations like listing channels or checking connection status. It's quite a robust configuration hub.
Okay, so once the channels are connected via the channel management service, we need something to actually do the work of syncing the data back and forth. That leads us naturally to the platform sync service. This sounds like the active workhorse, the engine continuously synchronizing data between Shiprocket and all those connected e-commerce channels.
Exactly. This is where the rubber meets the road for data integration. Its observed functions include webhook processing. For platforms like Shopify and WooCommerce that send those real-time notifications we mentioned, this service is the one listening and reacting to them immediately.
So it catches those new order pings.
Right. But for platforms like Amazon and Flipkart, which often don't provide such granular real-time webhooks, it employs a robust polling mechanism. It has scheduled jobs that periodically reach out to these platforms, say, every 15 minutes and ask any new orders since the last time I checked.
Got it. Pulling instead of waiting for a push.
Correct. It's also responsible for inventory sync, making periodic updates to product catalogs and, crucially, stock levels within Shiprocket based on data pulled from the seller's platforms. And, of course, order sync, pulling those new orders from all connected platforms into the main Shiprocket order service.
This sounds like a really complex orchestration task, given the sheer variety of platforms and the different APIs and capabilities.
Yeah.
What are some of its more advanced capabilities to handle this complexity reliably?
A key FANG-grade enhancement here must be per-platform resilience policies. Each e-commerce platform behaves differently. They have different API rate limits, different error responses, different maintenance windows. This service absolutely needs to implement custom retry logic and exponential back-off strategies tailored specifically for each platform.
So it knows how to handle a Shopify hiccup differently from an Amazon hiccup.
Exactly. This ensures that temporary failures or rate limit hits on one platform don't cascade or lead to permanently missed data. It also maintains stateful sync checkpoints. For every single store connection, it tracks the timestamp or ID of the last successfully synced order or inventory update.
Ah, so it knows where it left off.
Precisely. If a sync job fails midway or the service restarts, it knows exactly where to resume from, preventing data duplication, like pulling the same order twice, or data omissions, missing orders that came in during the failure. It also likely uses a schema registry.
Schema registry for managing data formats.
Yes. Different platforms send order data or product data in slightly different formats, different field names, different structures. A schema registry helps manage these different incoming data structures and provides a mechanism to transform them consistently into a canonical, standardized Shiprocket order model that the rest of the internal systems can understand.
That schema registry sounds vital for maintaining a consistent internal view of data, regardless of the source. Now, for something as absolutely critical as inventory, especially when a seller might be selling the same product on multiple platforms, how does this service handle potential conflicts? Like, what if an order comes from Shopify and Amazon for the last item at the same time?
This is where it gets truly sophisticated, and our inference points towards a very robust approach. For inventory consistency, especially across multiple active selling channels, this service likely uses a vector clock algorithm.
Okay, vector clocks again. Remind us how they work and why they're better than just timestamps here.
Right. So, unlike a simple timestamp, which just says, this update happened at time X, a vector clock tracks the history of updates across different locations, in this case platforms. For each inventory item, instead of one timestamp, it maintains a map or vector, like platform A, timestamp A, platform B, timestamp B, platform C, timestamp C. When an update comes in from, say, platform A, its timestamp in the vector clock is incremented. When comparing two vector clocks for the same item, you can determine not just which one is later, but whether one update happened before the other in a causal sense, or if they happen concurrently and potentially conflict.
Ah, so it understands the sequence of events across systems, not just the wall clock time.
Exactly. This allows for much more precise conflict detection and enables sophisticated conflict resolution policies. For instance, it can implement last right wins, but based on the causally determined latest timestamp within the vector clock. More importantly, it can detect true concurrent updates that a simple timestamp might miss, preventing situations where one update accidentally overwrites another that happened almost simultaneously on a different platform. For really critical inventory updates where preventing overselling is paramount, it might even use distributed locks via Redis red lock during the update process. This ensures that only one sync process can modify a specific SKU's record at any given moment, especially if two concurrent updates lack a clear causal link.
So vector clocks give you that causal history, which is much more robust for preventing loss updates or overselling. How does it manage the sheer volume of all these sync operations happening constantly?
For concurrency handling, it almost certainly uses sharded worker pools. This means sync jobs for different stores or sellers are processed in parallel by different groups of workers, ensuring that one slow sync operation, maybe due to a sluggish platform API, doesn't block syncs for other sellers.
Divides the work up.
Correct. It also implements adaptive concurrency control. It dynamically adjusts the number of concurrent API calls it makes to each specific platform based on that platform's current API rate limits and responsiveness. Often, this uses token bucket algorithms internally to ensure it stays within the allowed quotas for each platform API.
Smart throttling per platform.
Yes. The capacity estimates here are pretty impressive. We're talking potentially 8 million orders synced daily and another 8 million inventory updates synced daily. This likely utilizes a database of around 1.2 terabytes just for the operational data needed for syncing, like those checkpoints, probably retaining data for about 30 days. And it could be running over 200 concurrent sync jobs at any given time. It scales primarily based on polling intervals, like 15 minutes, but webhooks can provide near real-time updates on top of that.
That's a truly powerful and intelligent synchronization engine. Now let's shift gears slightly and talk about something absolutely fundamental to any shipping operation. Addresses. Shiprocket has a dedicated addresses service entirely focused on managing shipping and billing addresses, with a keen eye on that integrated GST compliance we mentioned earlier.
Correct. Addresses are foundational. Its API-validated functions include PAAC v1 external addresses to create a new address record. Critically, this process includes GST validation. The GST is India's Goods and Services Tax Identification Number, and validating its format and, ideally, its existence is essential for business compliance in India.
Right, got to get the tax info correct.
Exactly. It also offers GTV1 external PIN code. This endpoint is used to check PIN code serviceability. Basically, can Shiprocket's carriers deliver to this specific postal code? It often returns information about which carriers serve that PIN code, maybe estimated delivery times, or if it's even serviceable at all. The service also validates the GSTN format during address creation.
Okay. Now, a critical reality check here.
Right.
Based on the observable behavior. The service doesn't seem to offer address autocorrection or standardization, so the accuracy of the address largely depends on the seller providing good data.
That's a fair assessment. It primarily validates format and serviceability.
And it's strictly India-focused, meaning no validation for international addresses or foreign tax IDs. But its FA-grade enhancements demonstrate some clever optimizations, right?
Indeed. It likely uses a substantial PIN code serviceability cache, maybe a 200 gigabyte Redis cache to store frequently accessed PIN code serviceability information. Checking serviceability often requires calling external carrier APIs, which can be slow and rate limited. Caching these results dramatically reduces those external calls, speeding up order creation and carrier selection significantly.
Huge performance boost.
Definitely.
Yeah.
It also probably includes address template management, allowing sellers to save frequently used pickup or delivery addresses for quick selection later. And as mentioned, it integrates directly with India's official GSTN API for real-time GSTN verification, ensuring not just format validation, but actual verification against the government database for compliance.
Okay, and for ensuring the integrity of this address data itself, how does it handle potential concurrent updates to the same address record?
For concurrency control on address updates, the service likely primarily uses optimistic concurrency control, OCC, with version numbers.
OCC again, so check the version before updating.
Exactly. Imagine an address record has a version number, say V1. When a client reads it, they get V1. When they send an update request, they include V1 in the request. The service checks, is the current version still V1? If yes, apply the update and increment the version to V2. If the current version is already V2, meaning another update happened concurrently, the update request is rejected, typically with a 409 conflict status code. The client is then expected to refetch the latest version, V2, and retry their update.
Got it. Assumes conflicts are rare, detects them if they happen.
Right. However, for certain critical operations, like that real-time GSTN validation call, which might be rate-limited externally, it could employ distributed locks via Redis redlock. This would prevent multiple concurrent validation requests for the exact same GSTN from overwhelming the external GSTN API or causing inconsistent results.
The capacity estimates for this addresses service are quite telling. It likely stores over 50 million address records, processes maybe 1.5 million address validations or serviceability checks daily, and aims for a response time well under 100 milliseconds for address creation, which is vital for a smooth user experience during order entry. Next up in our tour is the product service. This sounds like it functions essentially as a centralized, mostly read-only cache of a seller's product catalog information.
Correct. That's a good way to think about it. Its primary API-validated function is GET V1 external products, which simply lists the products that have been synced into Shiprocket, typically from the seller's e-commerce platforms via that platform sync service we discussed. Crucially, the service provides essential details needed for shipping calculations and compliance. Things like product weight, dimensions, length, width, height, and HSN codes.
HSN codes, those are the harmonized system of nomenclature codes used for classifying goods for GST, right?
Exactly. Getting those right is vital for correct taxation and customs documentation within India.
Okay. Now, a critical distinction here, as you hinted. This service manages static products data, the relatively unchanging characteristics of a product like its name, SKU dimensions, HSN code. This is completely separate from the dynamic stock levels or inventory counts, which are handled by the inventory sync service.
Yes, that separation of concerns is important. This is about the product definition, not its current availability.
But even for static data, it comes with some excellent FA-grade enhancements, doesn't it?
Absolutely. It offers robust HSN code management, not just storing the codes, but likely validating their format and possibly ensuring they are appropriate for the product category, aiding GST compliance. It also performs product dimension validation. Carriers have strict rules about maximum package size and weight, so this service ensures the product dimensions recorded are compliant, preventing issues later during shipping. Furthermore, it plays a role in catalog synchronization, helping maintain a consistent view of product definitions across all connected platforms, even though the ultimate source of truth for product data usually remains the seller's primary e-commerce store.
How does it handle concurrent updates to this catalog data? Maybe a seller updates product dimensions on their store and that syncs across. How does it prevent inconsistent states, especially for high-traffic products?
That's a good question. For concurrency control on product catalog updates, it likely employs pessimistic locking.
Pessimistic locking. So it locks the record before updating.
Yes. When an update request comes in, likely triggered by the sync service, it would acquire an exclusive database lock on that specific product record before applying the changes. This prevents any other process from reading potentially stale data or writing conflicting updates to that same product record until the lock is released upon successful update completion. This ensures data integrity, especially for critical fields like dimensions or HSN codes.
That provides stronger guarantees than OCC, but potentially lower throughput.
Potentially, yes, which is why for extremely high traffic products, imagine a SKU that's part of a flash sale and getting updated frequently, it might implement lock striping.
Lock striping again. Break the lock into smaller pieces.
Exactly. Instead of one global lock for all products, or even one lock per product, which could still be a bottleneck for a very popular product, it divides products into multiple logical lock groups, say 16 groups, based on hashing the product ID, hash producted 16. Updates only need to acquire the lock for their specific group. This dramatically reduces contention by spreading the locking load across multiple independent locks. It also probably uses write-through caching with Redis. This means when a product record is updated in the database, the corresponding entry in the Redis cache is immediately updated or invalidated as part of the same transaction. This ensures that the cache stays consistent with the database, providing fast, reliable reads of product data.
Looking at its capacity estimates, this service is built to handle a massive scale. Potentially over 100 million SKUs across those 500,000 plus seller accounts. This might require a 2 terabyte database just for the product catalog definitions. It needs to support around 500 requests per second for product lookups, which are frequent during order processing, and maintain a high, maybe 99.9% success rate for product validation against carrier rules. It demonstrates its efficiency and importance. Now we arrive at what feels like the absolute heart of the Shiprocket platform, the order service. This is the core domain service, the definitive authority on an order's state and lifecycle within the entire Shiprocket ecosystem.
Absolutely. If any service is central, it's this one. Its API-validated functions are fundamental to the whole operation. You have POSD V1 external orders create for standard single order creation, create Hawk for creating orders on the fly without a pre-existing product catalog entry perhaps, and create bulk for uploading multiple orders at once. These are all synchronous endpoints.
Synchronous, meaning you get an immediate success or failure response.
Correct. Then there's POS V1 external orders cancel, which is designed as an atomic operation and requires a cancellation reason. And of course, DAT V1 external orders show ordered to retrieve all the details about a specific order. Significantly, before it even attempts to create an order record, it performs critical precondition checks. It makes synchronous gRPC calls, that's Google's high-performance remote procedure call framework, good for fast internal communication to the account service to check if the seller has sufficient balance, and to the product service to ensure the SKUs in the order actually exist and have valid dimensions. Only if those checks pass does it proceed.
So it validates prerequisites up front. Gosh, smart. Now, for the critical reality check. This service performs no inventory reservations itself. It only checks if the product exists in the catalog, not if it's in stock. And as we've established, no payment processing for the end customer. That's handled externally by the seller's platform. However, its AFANG-grade enhancements seem deeply sophisticated, especially around achieving scalability and that crucial financial integrity.
Indeed. For massive scalability, it almost certainly uses database sharding. The order data is horizontally partitioned, most likely sharded by seller ID.
Sharding by seller ID. So each seller's orders might live on a different physical database server or cluster.
Exactly. This allows the system to scale horizontally almost indefinitely by adding more shards as the number of sellers grows. It prevents any single database instance from becoming a bottleneck. It also implements idempotency logic, working hand in glove with that idempotency key checked by the API gateway. This ensures that if a create order request is retried, it doesn't result in a duplicate order record, guaranteeing that once an order is successfully created, it remains unique.
Okay, and this is where that balanced reservation pattern we discussed earlier becomes absolutely critical in the order service's workflow, right?
Sure.
It's not just the account service, the order service initiates it.
Precisely. This pattern is orchestrated partly by the order service and is crucial. It's that reserve capture pattern designed to prevent financial race conditions. When the order service receives a creation request and the initial product checks pass, its next step is to make that synchronous call to the account service to attempt to reserve the estimated shipping amount. If that reservation attempt fails, maybe the seller just ran out of credit, the order creation process fails immediately and atomically right there. The order record is never created.
Stops it dead in its tracks.
Yes. Only if the reservation succeeds does the order service actually create the order record in its database. Later, when a shipping label is generated by the label service, a different process triggers the account service to convert that reservation into a final debit, the capture. And if the order is canceled by the seller before a label is generated, the order service notifies the account service to release the reservation.
Wow. That's a complex, multi-step, distributed transaction, essentially, just orchestrated carefully without relying on, say, XA transactions.
Exactly. It adds architectural complexity, more communication between services, but it's absolutely essential for maintaining financial integrity in their prepaid model. It prevents situations where a seller might appear to have funds at the moment of order creation, but not have them available when the actual shipping charge needs to be applied later.
That's a truly elegant solution to a very tricky distributed systems problem. Okay, for concurrency control, more broadly within the order service, how does it handle multiple updates happening at once?
It uses a mix of strategies. For general status updates on an order, like moving from processing to manifested, it likely uses optimistic concurrency control, OCC, with version numbers. This ensures that if multiple processes try to update an order's status simultaneously, only the one working with the freshest data succeeds, preventing lost updates. We already mentioned idempotency keys, often stored in Redis, are crucial for the creation process to prevent duplicates. For order cancellation, which is a particularly sensitive state change, it probably leverages distributed locks, using Redis Redlock, to ensure that only one cancellation request for a given order can be processed at any single moment.
Locks down the cancellation process.
Right. During peak events like massive sales, it likely applies adaptive concurrency throttling to prevent its own database shards from getting overwhelmed. And it uses efficient database connection pooling with a library like Hikara CP to manage connections to its database shards effectively. It's also rigorously designed for thread safety internally, using stateless methods where possible, immutable data structures for critical order data, and thread local storage for things like request context or trace IDs.
The capacity estimates truly underscore the immense scale this service operates at, potentially processing 2 million orders daily, leading to a historical data store of over 60 billion order records. This requires a massive 15-terabyte database, carefully sharded by Celerid. Each shard needs to handle a peak load of perhaps 1,000 requests per second, and the service boasts an exceptional 99.95% success rate for order creation, highlighting its reliability. Okay, so after an order is successfully created by the order service, the next crucial step is figuring out which carrier should actually handle the shipment and assigning it. That sounds like the job of the courier service.
Correct. This service is all about carrier selection and assignment. Its API-validated functions include GTT v1 external courier list with count. This endpoint lists all the carriers Shiprocket integrates with, possibly along with counts of how many shipments are currently pending pickup for each one, giving sellers some operational visibility. It also offers GTV1 external courier serviceability. This is used frequently to check if a specific origin pin code and destination pin code pair is serviceable by a given carrier, and often returns estimated costs and delivery timelines for that carrier.
So you can compare options.
Exactly. And finally, POST v1 external courier SUNOB is the action endpoint used to actually assign a specific carrier and often retrieve an airway bill number, or AWB, to a specific shipment ID that was created by the order service.
Okay, now a critical reality check here. Based on the API structure, this service focuses purely on serviceability checking and assignment. It doesn't handle the actual generation of the shipping label or the tracking of the shipment once it's in transit. Those functions belong to the label service, which we'll get to next.
That's right. Clear separation of concerns.
But the ECAN grade enhancements for this courier service seem to be all about intelligence and optimization, making the best choice, not just choice.
Exactly. It likely uses carrier performance scoring. It's constantly tracking operational metrics for each carrier, things like their actual on-time delivery percentage for different routes, their rate of non-delivery reports, NDRs, their pickup success rates, maybe even customer feedback scores.
Collecting data on how good they actually are.
Right. And this data feeds directly into a dynamic carrier selection algorithm. When a seller requests serviceability or needs a carrier assigned, this service doesn't just list options. It often recommends the optimal carrier based on a combination of factors: cost, estimated delivery time, and that historical performance score. This recommendation can often be customized based on the seller's own priorities. Example, always prioritize speed over cost.
Smart recommendations.
It also incorporates a carrier-specific rules engine. Every carrier has its own unique set of rules: maximum weight limits, restrictions on certain types of products like hazardous materials or liquids, specific PIN codes they don't service. This engine enforces those rules during the serviceability check and assignment process, preventing invalid assignments that would fail later.
So it's not just selecting, it's validating against complex rules. How does it manage the sheer complexity of actually talking to so many different carrier systems?
This is where deep carrier API integration comes in. It involves directly using official SDKs, software development kits, provided by carriers like FedEx, or building custom REST, or even XML clients to interact with the APIs of carriers like Delivery or Blue Dart. This includes implementing highly specific, carrier-specific rate limiting logic. For instance, knowing that FedEx might limit you to 50 API calls per minute requires a token bucket algorithm configured specifically for them. Knowing Delivery might return 429. Too many request errors requires implementing exponential back-off retry logic just for delivery calls. Maybe Blue Dart requires careful request queuing. It's very granular.
Tailored handling for each carrier's quirks.
Absolutely. It likely makes parallel API calls when checking serviceability for multiple carriers simultaneously to speed up comparisons, and critically, it employs circuit breakers using libraries like Resilience4j for each individual carrier integration.
Circuit breakers.
Yeah.
Yeah, those stock calls if a system is failing, right?
Exactly. If, say, the delivery API starts returning lots of errors, the circuit breaker for delivery opens, and the courier service temporarily stops sending requests only to delivery, preventing cascading failures and giving delivery system time to recover. Requests to other carriers like FedEx continue normally.
That's vital for overall system resilience when dealing with so many external dependencies. Now, how does it ensure no duplicate assignments happen or avoid conflicts if multiple requests try to assign a carrier to the same shipment simultaneously?
For concurrency control around the critical assignment step, it likely utilizes distributed locks, probably using Redis. When a request comes in to assign a carrier to shipmented 12D3, it first acquires a lock specific to that shipment ID. This prevents any other concurrent request from trying to assign a different carrier to the same shipment at the exact same time, ensuring atomicity. It also employs adaptive concurrency limits per carrier, dynamically adjusting how many simultaneous requests it sends to a specific carrier's API based on their observed performance and rate limits. And where carrier APIs support it, it uses request batching to consolidate multiple queries, like checking serviceability for several PIN codes, into a single API call, reducing overhead.
This service is juggling integrations with maybe 30-plus different carriers, potentially making 5 million carrier API calls every day, and relying on a huge, maybe 1.5 terabyte cache for that serviceability data. The goal is a high, maybe 95% successful assignment rate on the first try. Okay, so the courier service has picked the best carrier and assigned the shipment. The next logical step is actually generating the physical shipping label that goes on the package. That's the responsibility of the label service.
Indeed. This is where the digital meets the physical preparation. Its primary API validated function is POST V1 external courier generate label. Interestingly, this is specified as a synchronous endpoint.
Synchronous, so the client calls it and waits for the label.
Yes, the API response itself contains a label URL, which is a direct link to download the generated shipping label image or PDF. The client waits for this URL. It also offers getT V1 external courier track shipmented, which acts as a unified interface for tracking shipments. Behind the scenes, this service pulls carrier tracking APIs or listens for tracking update webhooks sent by the carriers. Crucially, it ensures that the generated labels meet all the very specific formatting requirements of the assigned carrier: barcodes, addresses, service codes. Everything has to be perfect.
Got it. Now, for the critical reality check, as you said, there's no asynchronous label generation exposed via the public API. The client call blocks until the label URL is ready. Also, that label URL provided is temporary, usually only valid for maybe 24 hours, likely stored in something like S3 with a short expiry.
Correct, on both points, practical limitations.
But the FN-grade enhancements seem focused on resilience and correctness when dealing with those external carrier APIs for the actual booking and label generation.
Absolutely. Given the dependency on external systems, resilience is key. It uses carrier-specific circuit breakers, similar to the courier service, but specifically for label generation APIs. If the FedEx label API fails, the FedEx label circuit opens, but label generation for delivery continues unaffected. It likely features adaptive timeouts, dynamically adjusting how long it waits for a response from a carrier's label API based on historical performance or current system load, preventing indefinite hangs.
Smart adjustments.
And label URL expiry enforcement is automated. There's probably a background job plus an S3 lifecycle policy that automatically purges those temporary label image files from cloud storage after their expiry period, like 24 hours, to manage costs and keep things tidy.
And what about the actual interaction with the carrier to book the shipment and prevent errors there? That seems critical.
Yes, it handles the carrier API booking step. This is where it officially tells the carrier system, okay, we're confirming this shipment, please generate the label and tracking number. Critically, for this booking step, it absolutely must implement idempotency keys.
Idempotency again, but specifically for the booking call to the carrier.
Yes, this is vital for financial integrity and operational correctness. You do not want to accidentally book the same shipment twice with the carrier, which could lead to double charges or duplicate pickups. By sending a unique idempotency key with the booking request, the label service ensures that even if the request is retried, the carrier processes it only once. It also needs sophisticated handling for various carrier-specific errors during booking and implement custom retry logic only for transient recoverable failures.
Okay. And for concurrency control within the label service itself, how does it prevent multiple requests trying to generate a label for the same shipment ID at the same moment?
Similar to carrier assignment, it uses distributed locks, Redis red lock likely, for the label generation process, keyed by the shipmented. This ensures that only one process can attempt to generate a label for a specific shipment at any given time, preventing duplicates or inconsistent states if, say, two requests came in very close together. It also employs request queuing during peak load periods to avoid overwhelming the downstream carrier APIs, and uses batch processing for label generation if any carriers support that. Optimistic concurrency control, OCC, is probably used for updating the tracking status internally as updates come in from carriers.
This service is a real workhorse, too, generating perhaps 1.8 million labels daily. This requires significant temporary storage, maybe 43 terabytes on S3, even with just 24-hour retention. It needs to handle peaks of around 800 label generation requests per second and aims for a very high 99.9% generation success rate, which speaks to its resilience and error handling capabilities. All right, beyond successful deliveries, a massive part of modern e-commerce logistics is handling returns efficiently. That's where the return management service comes into the picture.
That's right. Reverse logistics can often be even more complex and costly than forward logistics, so having a dedicated service makes sense. This service manages the entire reverse logistics workflow from initiation to completion. Its primary API-validated function is POST V1 External Orders Return Create, which allows a seller, or their customer via the seller's platform, to initiate a return request for an order. It then coordinates internally with the label service to generate the necessary return shipping labels and meticulously tracks the return shipment status via updates from the carrier, providing visibility throughout the often lengthy return journey.
Okay. Now, for the critical reality check, this service manages the logistics of the return, but it doesn't process automatic refunds. The actual refund to the end customer is a separate process, typically handled by the seller on their e-commerce platform after Shiprocket confirms the return has been successfully received and inspected.
Correct. It facilitates the return, not the refund itself.
Also an interesting detail, the API consistently uses the singular form return in its endpoints, like orders return create, not returns, just a naming convention observation. But the N-grade enhancements here seem quite extensive, really modeling a complex business process.
Indeed. It likely implements a robust state machine internally to model the return lifecycle formally. This means a return progresses through well-defined, distinct states. Maybe requested, then pickup scheduled, in transit delivered back to seller, QC pending, quality check, and finally completed or rejected.
Using a state machine makes the process much more structured and auditable, right? Prevents invalid transitions.
Exactly. It ensures the return follows a logical flow. It also probably features a return eligibility engine. Before even creating a return record, this engine checks if the product is actually eligible for return based on seller-defined policies, things like the return window, firstly within 30 days of delivery, product category restrictions, or reason codes.
So sellers can configure their own specific return rules.
Precisely. And crucially, while it doesn't process the refund, it handles refund coordination. Once a return reaches a final approved state, for example after QC, this service likely triggers a notification or an API callback to the seller's e-commerce platform, signaling that it's now okay to issue the refund to the customer. It also performs the carrier return booking, interacting directly with carrier APIs to schedule the pickup of the return package from the customer.
Okay, how does it manage concurrency control for returns? What if multiple updates happen regarding the same return?
It likely uses state-based concurrency. Often this involves using exclusive locks, maybe database level or distributed locks, specifically when transitioning between major states, ensuring only one process can action a state change at a time. It would also use idempotency keys for the initial return creation request, distributed locks for the sensitive step of scheduling the return pickup with the carrier, and optimistic concurrency control, OCC, for less critical status updates within a state.
This service handles a significant volume, maybe 300,000 return requests daily, requiring perhaps a 5 terabyte database just for return records and their history. It needs to be designed for around 200 return creation requests per second, aiming for a high, maybe 99.5% processing success rate, highlighting its capability to manage large-scale reverse logistics efficiently. Next, we encounter a service that's particularly critical, almost a differentiator, in the challenging Indian logistics market, the NDR management service. NDR stands for non-delivery report, and this service handles the often high-stakes workflow when a delivery attempt fails.
Absolutely. Non-delivery is a common and very costly problem in logistics everywhere, but especially challenging in markets with complex addressing schemes or high rates of cash on delivery, COD, which is prevalent in India. Failed deliveries lead to returns, unhappy customers, and wasted shipping costs.
So this service tries to manage that proactively.
Yes. Its API-validated functions include YITI v1 external Andrew manifest, which lists all shipments currently in an NDR state, delivery failed, awaiting action, and POS v1 external interaction allows sellers to provide instructions on how to resolve the NDR. Common actions are reattempt delivery or return to origin, RTO. Its core function is automated NDR detection. It constantly monitors tracking events coming in from carriers. When it sees a status like delivery attempt failed, customer not available, or incorrect address, it automatically creates an NDR record in the system and likely notifies the seller, ensuring no failed delivery goes unnoticed and requires action.
Okay, so it flags the problems. The M-grade enhancements here seem quite sophisticated, leveraging data and even machine learning to tackle this thorny problem more proactively.
They really do. There's likely some form of predictive NDR prevention. This could involve an ML model trained on historical data to predict the likelihood of an NDR before a shipment even leaves the warehouse. It might look at factors like the quality score of the delivery address, the historical NDR rate for that specific PIN code, the value of the shipment, or if it's a side order, which statistically have higher NDR rates.
So it flags high-risk orders for review upfront.
Exactly. It allows sellers to potentially intervene early, maybe call the customer to confirm the address or delivery time for high-risk orders, trying to prevent the NDR from happening in the first place. It also includes automated resolution rules. Sellers can configure predefined actions for common NDR reason codes. For example, if NDR reason is customer not available, automatically schedule one reattempt. This reduces manual effort for common scenarios.
Smart automation.
And an NDR analytics dashboard likely provides sellers with insights into why their shipments are failing delivery, which PIN codes are problematic, which NDR reasons are most common, helping them optimize their own operations or packaging.
That's a really powerful use of data to not just react to, but actively try and prevent problems.
Yeah.
How does it handle concurrent resolution actions? Like, if two people in the seller's team try to resolve the same NDR simultaneously with different actions?
Good question. For concurrency control on the resolution step, it almost certainly uses pessimistic locking. When a user initiates an action like reattempt on a specific NDR record, the system acquires an exclusive lock on that record. This prevents any other user or automated process from submitting a conflicting action, like return to origin, until the first action is completed and the lock is released. This ensures a single, consistent resolution per NDR. It also needs idempotency keys for the action submissions themselves and robust event deduplication, likely using Redis, for the initial NDR detection, ensuring that multiple identical delivery failed events from a carrier for the same tracking number don't create duplicate NDR records. During high-volume periods, it might also use adaptive processing rates for handling incoming NDR events to prevent system overload.
This NDR service is managing perhaps 50,000 NDR cases daily, requiring maybe a 500 gigabyte database just for NDR records in history. It needs to support around 50 resolution actions per second and aims for an impressive 98% automated resolution rate thanks to those rules, which represents a significant operational efficiency gain for sellers. Okay, after all the individual shipments are assigned carriers and maybe have labels generated, they often need to be grouped together for the physical handover to the carrier driver. This is where the manifest management service comes into play.
That's right. Especially for sellers shipping larger volumes, carriers often require a manifest, essentially a list or summary document detailing all the packages being handed over in a single pickup batch. Its API-validated functions include POST-V1 external manifest generate. This call takes an array of shipmentids that are ready for handover to a specific carrier and generates a manifest document, often a PDF, that includes details for all of them. It also offers get v1 external manifest to retrieve the status or download URLs for previously generated manifests. A crucial part of its job is manifest validation. It ensures that the group of shipments being manifested together meets any carrier-specific requirements. For example, some carriers like Delivery might mandate a minimum of, say, 5 shipments per manifest for a pickup.
So it enforces carrier rules at the batch level. The FANG grade enhancements here seem focused on streamlining this bulk handover process and preventing errors.
Precisely. It likely uses an automated carrier rules engine to validate all the shipments included in a manifest request against the specific carrier's rules before attempting to generate the manifest document. This prevents generating manifests that would be immediately rejected by the carrier at the time of pickup due to non-compliant shipments.
Catches errors early.
Yes. It also probably features manifest expiry tracking, maybe manifests that are generated but never actually used for a pickup within, say, 24 hours are automatically marked as closed or expired. This is good for operational hygiene and prevents stale manifest data from cluttering the system. Manifest consolidation logic might also exist to intelligently group shipments going to the same carrier and perhaps similar destinations onto optimal manifests, potentially simplifying the carrier's sorting process later.
Okay. And for preventing issues when multiple manifests might be generated concurrently, perhaps for the same set of shipments or by different users, how does it ensure consistency?
For concurrency control, the manifest generation process itself likely relies on distributed locks, probably Redis red lock again, perhaps keyed by the carrier and seller ID for a given day. This ensures that only one process can generate the next manifest for that carrier-seller combination at a time, preventing duplicates or race conditions in assigning shipments to manifests. For updating the status of a manifest, for example, from generated to picked up, it would likely use optimistic concurrency control, OCC. And for high-volume sellers generating many manifests, it might employ batch processing internally and request queuing to manage the load smoothly. This ensures that manifest creation is treated as an atomic and consistent operation.
This service is handling maybe 200,000 manifests daily, supported by perhaps a 1 terabyte database for manifest records in history. It needs to manage around 100 manifest generation requests per second, aiming for a very high 99.8% creation success rate, indicating a highly reliable process for this critical handover step. And finally, to complete the physical logistics loop, connecting the digital plan with the real world, we have the pickup management service. This sounds like it orchestrates the actual scheduling and tracking of carrier pickups from the seller's warehouses or locations.
Absolutely. This is where the digital instructions translate into a truck arriving at the seller's door. Its API-validated functions include POST V1 external carrier generate pickup. This is used to create a pickup request, specifying the desired date and time slot, and crucially, an array of shipmentids that are ready and manifested for that specific carrier to collect. It also offers GET-V1 external courier generate pickup to retrieve the schedule or status of pending or completed pickups. A key part of its role is pickup window management, handling the availability of pickup time slots offered by different carriers in different locations.
Okay, now a really critical reality check for this service, as you mentioned earlier. It often requires human-in-the-loop approval from the seller. The seller typically has to explicitly confirm in the Shiprocket interface that the packages are ready before the pickup is finalized and scheduled with the carrier. And you cannot schedule a pickup via the API without providing those specific shipmentids that are ready to go.
Correct. This prevents scheduling pickups for packages that aren't actually ready, which would waste the carrier's time and the seller's money. It ensures seller confirmation.
Makes sense. However, it still incorporates some smart FANG-grade enhancements to optimize the process, right?
It does. It likely uses automated pickup optimization. For sellers with high volumes, instead of scheduling one pickup for every single manifest, it might intelligently group nearby shipments or manifests going out on the same day to the same carrier into a single, larger pickup request. This minimizes the frequency of carrier visits, reducing operational overhead and potentially costs for both Shiprocket and the carriers.
So it's not just scheduling. It's trying to do smart, consolidated scheduling.
Exactly. And there's that clear seller approval workflow step integrated, ensuring explicit confirmation before the final booking with the carrier. It also provides pickup status tracking, monitoring the execution of the scheduled pickup. Did the carrier arrive on time? Was it successful? Were there any issues reported, and alerting sellers if problems arise?
Okay. And for concurrency control here, how does it prevent, say, double booking a pickup for the same set of shipments?
It definitely employs distributed locks for the critical step of scheduling the pickup with the carrier. The lock would likely be based on the seller, carrier, and date-time slot combination, preventing multiple simultaneous requests from trying to book the same pickup slot or include the same shipments in concurrent requests. For updating the pickup status later, it would use optimistic concurrency control, OCC. It likely applies adaptive scheduling algorithms during peak times and utilizes idempotency keys on the API endpoint to prevent duplicate pickup requests from being created accidentally.
This service optimizes its performance by caching frequently used pickup locations and integrating directly with carrier-specific APIs for scheduling availability and booking, ensuring efficient and reliable pickup operations, which is crucial for the start of the physical journey.
Phew. Okay, let's switch gears now to arguably one of the most critical internal components, the account service. This manages all the seller account information, but most importantly, it handles the financial transactions. It's the absolute authoritative source for the seller's prepaid shipping credits.
This service is absolutely central to Shiprocket's entire business model. Its API-validated functions reflect this. There's DTV1 external account credit balance for sellers to check their real-time available balance. There's DTV1 external account transactions to get a detailed, itemized history of all debits, like label charges, and credits, like top-ups. And BTV1 external account profile for fetching general account details. It is specifically designed around managing those prepaid shipping credits, which is the primary way sellers pay for Shiprocket services. Right, the prepaid model is key. Now, for the critical reality check. As we've stressed, Shiprocket doesn't do direct payment processing itself, like handling credit cards for top-ups. It only coordinates with external payment gateways for that. Therefore, it's not within PCI DSS scope, as it never touches or stores raw credit card information.
Correct. It manages the balance, not the payment method.
And they're very clear about the terminology. It's a credit balance, not a wallet, which might have different regulatory implications. But for the FN grade enhancements, this is where financial integrity or robustness are absolutely paramount.
Without a doubt. The foundation is an ACID-compliant ledger. This is almost certainly built on a reliable relational database like PostgreSQL, which guarantees ACID properties, atomicity, consistency, isolation, durability for transactions. Critically, it uses double-entry bookkeeping for every single financial transaction.
Double-entry bookkeeping,
Yeah.
like accountants use.
Exactly. Every financial event results in at least two entries, a debit in one account and a corresponding credit in another. For example, generating a label might debit the seller's credit balance account and credit an internal shipping revenue account. This ensures the books are always balanced, debits always equal credits, and provides a complete auditable trail for every rupee, which is crucial for financial accuracy and compliance.
That's fundamental for financial systems.
Yes. It also provides real-time GST compliance, integrating directly with India's GSTN APIs to generate legally compliant e-invoices for the shipping services provided to sellers. It offers balance threshold alerts, automatically notifying sellers via email or SMS when their credit balance drops below a certain configurable level, prompting them to top up before their service gets interrupted.
And this is where that balance reservation mechanism, that reserve capture pattern, really comes into its own, implemented within the account service itself to prevent those critical financial mishaps. Can you walk through that again from the account service's perspective?
Absolutely. It is the cornerstone of their financial control. When the order service, or potentially another service, requests a reservation for an estimated shipping cost, the account service attempts to atomically decrease an available balance while increasing a reserved balance for that seller, all within a single database transaction. If the seller's available balance is insufficient, this transaction fails and the reservation is denied. Later, when the label service confirms a label has been generated, it sends a capture request. The account service then executes another transaction to decrease the reserve balance and decrease the actual balance, effectively finalizing the debit. If an order is canceled before capture, a release request comes in, and the account service simply decreases the reserve balance and increases the available balance back.
So the actual balance only decreases upon capture, but the available funds are reduced upon reservation.
Precisely. This meticulously managed pattern, enforced with AC transactions within the account service, is what prevents overspending and guarantees atomicity for these crucial financial operations, even under high concurrency.
That detailed choreography is seriously impressive. Okay. For concurrency control across all these sensitive financial operations within the account service.
It has to be extremely robust.
Mhm.
It primarily uses pessimistic locking at the database level for any operation that modifies a seller's balance. When a transaction needs to update a seller's balance record, it acquires an exclusive lock on that specific row using select for update. This physically prevents any other concurrent transaction from even reading, in some modes, or writing to that seller's balance record until the current transaction completes, commits, or rolls back.
Guarantees exclusive access during the update.
Yes, it absolutely guarantees against ref conditions like negative balances or lost updates, which is non-negotiable for a financial ledger. They likely use a short timeout, or example 5 seconds, on the lock acquisition to prevent indefinite deadlocks. As mentioned, double entry bookkeeping is enforced with full transactional integrity. For performance, they might use request batching for certain high-volume internal operations, like applying end-of-day fees. They might also leverage distributed locks, Redis Red Lock, for specific critical cross-service financial coordination scenarios, although the core balance update relies on the database lock. Furthermore, they likely implement accounting versioning, including a version number or sequence ID in each transaction record to help detect or prevent lost updates in complex scenarios. All financial operations happen within strict database transactions. Internally, the service uses thread-safe data structures for any in-memory caching or operations and ensures proper transaction sequencing for ordered financial events.
The capacity estimates truly reflect the heavy financial load the service carries. Potentially 1.2 million distinct financial transactions. Reservations, captures, releases, top-ups daily. This could lead to over 300 million transaction records historically, requiring maybe a 3 terabyte database. It needs to handle around 500 requests per second just for balance checks or transaction history lookups, and must achieve an exceptionally high, maybe 99.995% success rate for financial operations, demonstrating extreme reliability. Okay, our final core service to examine is the inventory sync service. Now, we talked about the platform sync service pulling data in. This inventory sync service sounds like it maintains Shiprocket's internal read-only cache of the seller's product inventory levels.
Exactly. It's important to understand its role clearly. It primarily serves as an internal cache used for validation or informational purposes by other services, like maybe showing stock levels in the UI or validating during order creation. Its API-validated functions likely include GET V1 external inventory for sellers to query the cache stock levels Shiprocket has recorded for their products. And internally, there's likely a PUT V1 external inventory update endpoint used exclusively by the platform sync service to push updated stock levels into this cache.
Right, so the platform sync gets the data from Shopify Amazon, then tells this inventory sync service to update its cache.
Precisely.
Now, the absolutely critical reality check here. This service makes no transactional reservations. It only reflects the last known stock level. It is not the source of truth for inventory. The seller's actual e-commerce platform, Shopify, Magento, etc., remains the definitive, authoritative source of inventory data. This service just holds a recent copy.
That distinction is vital. Shiprocket doesn't manage inventory, it syncs it for its own operational needs.
However, its FN-grade enhancements are designed for efficiency and accuracy in maintaining this synchronized cache.
Exactly. To handle the sheer volume of updates, it uses delta syncs and batch updates. The platform sync service likely calculates only the changes, deltas, in inventory levels, and this service processes just those changes rather than constantly reviewing entire inventory lists. These deltas are then often batched into larger updates to reduce the load on its own database and improve efficiency. It also likely offers inventory health monitoring, tracking sync success rates, latency, and discrepancy rates, proactively alerting internal teams or even sellers if inventory data seems consistently stale or problematic for a particular channel. Stock level thresholds can also be configured here, allowing Shiprocket to generate low stock alerts for critical products based on the cache levels, prompting sellers to replenish.
Okay, and we discussed vector clocks earlier in the context of the platform sync service, using them for robust conflict detection.
How does that sophisticated multi-platform inventory handling manifest here in the Inventory Sync Service's multi-platform inventory management capabilities?
Right. While the platform's sync service uses vector clocks to determine the correct update sequence, this inventory sync service is where the result of that logic is stored and potentially queried. It maintains that unified cached view across platforms. Each cached inventory record would store the latest quantity and the associated vector clock. For example, LESKU 123 QI 5 clock Shopify 15 Amazon 12. When other Shiprocket services need to check stock, perhaps as a non-binding check during order creation, they query this service. The vector clock stored here provides crucial context about the data's freshness and origin. While this service itself might not perform complex conflict resolution that happened in the platform sync, it holds the results of that resolution. The use of vector clocks here, propagated from the sync service, ensures that the cached view reflects the causally correct state derived from multiple potentially conflicting sources, offering much stronger consistency guarantees than simple timestamps would, justifying the complexity trade-off.
That level of detail, store the vector clock with a cached quantity, is impressive for ensuring consistency and traceability, even in a read-only cache. Now, for concurrency control within this inventory sync service itself, as it receives updates from the platform sync service.
Even though it's primarily a cache, updates need to be handled carefully. It likely utilizes distributed locks, Redis redlock, for updates to the same SKU coming in potentially concurrently from the platform sync service. Maybe updates from Shopify and Amazon arrive very close together. This ensures that updates to a specific iSKU's cached record are serialized, preventing race conditions during the cache write. It probably also uses optimistic concurrency control, OCC, with version numbers on its own database records. For high-traffic SKUs, it might even employ lock striping on its Redis locks to reduce contention during updates. When an order is being created, the order service might perform a quick pre-check with version validation against this service, reading the cache stock level and its version vector clock just as an informational check, though not a binding reservation. And it likely uses write-through caching with Redis for extremely fast reads of the cache stock levels.
In terms of capacity estimates, this service is managing cache data for potentially over 100 million SKUs, processing perhaps 8 million inventory updates daily fed from the platform sync service. It might use a 1.2 terabyte database optimized for writes, probably retaining data for maybe 30 days. The goal is to reflect changes with low latency, ideally less than 2-minute sync latency for updates coming via webhooks. Truly a robust system just for keeping this critical cached view in check.
Okay, that was an incredibly comprehensive tour of Shiprocket's core services, from the gateway right through to managing accounts and inventory caches. Now, let's go even deeper, peeling back another layer to look at the underlying data and eventing layer that makes this whole distributed system function reliably.
This is really the foundation upon which everything else is built. Their overall database strategy appears to be single-region, multi-AZ. Critically, for India data localization, all sensitive seller data resides exclusively within the AWS App South 1 region, which is Mumbai.
So all data stays within India's borders. Correct. For high availability, their databases, likely primarily PostgreSQL, maybe with some purpose-built databases too, are deployed across multiple availability zones, AZ, within that Mumbai region. AZs are essentially separate data centers with independent power and networking. This setup allows for automatic failover. If one AZ experiences an outage, the database traffic automatically shifts to a replica in another AZ with minimal disruption.
And their sharding strategy seems quite sophisticated, as we discussed for individual services.
It is. The primary sharding key for most core services like orders, account, and the inventory cache is Cellarid. This distributes the load very effectively as the number of sellers grows. Other services use different keys where appropriate. The courier service might shard some data by carrier, and the addresses service likely shards its pin code serviceability data by pin code. This tailored sharding optimizes performance for each service's access patterns.
What about backup and recovery? How do they protect against data loss?
They likely have a multi-layered approach. Continuous backups, using features like PostgreSQL's point-in-time recovery, PITR, allow them to restore the database to almost any specific second within the last, say, 35 days. They also probably take daily database snapshots, which are full copies stored for longer retention, maybe 90 days perhaps in S3, and cross-AZ replication provides that immediate failover capability, aiming for a recovery point objective, RPO, the maximum acceptable data loss of less than 5 minutes.
Okay, very robust protection. Now let's revisit concurrency control, but from the database layer perspective. How do these different models work together?
Right. They employ several standard database concurrency control mechanisms strategically. Optimistic concurrency control, OCC, is the workhorse for about 80% of their business entities, orders, returns, manifests, addresses, etc. As we covered, this uses a version column in the database table. Update statements include a where version updates clause. If the row is modified concurrently, the version won't match, the update affects 0 rows, and the application knows to retry. This is often handled transparently by ORMs like Spring Data JPA using the @version annotation. It's efficient when write conflicts are relatively infrequent.
And for the critical high contention stuff.
For truly safety-critical operations where conflicts cannot be tolerated, like the financial operations in the account service or maybe updates to extremely high-velocity inventory items, they switch to pessimistic locking. This uses explicit database locks, typically acquired via select, for update and PostgreSQL. This lock prevents any other transaction from modifying or sometimes even reading the locked rows until the current transaction commits or rolls back. They likely use a short lock timeout, purging 5 seconds, to prevent deadlocks. This is implemented via JPA using lockModeType.pessimistic write. It guarantees consistency at the cost of some concurrency.
And underlying all of this is PostgreSQL's own engine.
Exactly. They heavily leverage PostgreSQL's default multi-version concurrency control, MVCC. MVCC is ingenious because it allows different transactions to see different snapshots of the database as it existed at different points in time. This means readers generally don't block writers, and writers don't block readers. Each transaction operates on a consistent view of the data without needing explicit locks for reads. This is absolutely critical for allowing analytical or reporting queries to run alongside high-volume transactional workloads without crippling performance, providing what's known as snapshot isolation.
That MVCC capability is a huge benefit of using databases like PostgreSQL. Now, shifting to their caching strategy, Shiprocket clearly makes extensive use of Redis, likely in clustered configurations for scalability and availability. Can you tell us how they seem to organize their Redis usage?
Yes, based on the needs of different services, they appear to have a two-pronged approach, likely using separate Redis clusters for different purposes. There's a cache cluster dedicated primarily to caching frequently accessed, often read-only data to reduce database load. Think of that huge carrier serviceability cache, cached product catalog details, maybe results of GST validations. Reading from Redis is much faster than hitting the database.
Right, the read-heavy cache.
Exactly. Then there's likely a separate worker cluster. This Redis cluster is used more for managing operational state things required for real-time processing logic. This is where you'd find rate-limiting counters, like for the token bucket algorithm, storage for idempotency keys, and importantly, the distributed locks used by various services for concurrency control during background jobs or critical operations. This data is often short-lived but needs to be accessed extremely quickly.
Okay, two distinct roles for Redis. And how do they keep the data in that cache cluster fresh and consistent with the underlying databases?
Cache invalidation is a classic hard problem, and they likely use a mix of techniques. For data that changes periodically but not instantly, like maybe carrier rates, they might use simple time-based expiration, TTL, time to live. The cache entry is valid for, say, 5 minutes, after which it's automatically evicted, and the next request fetches fresh data from the source. For more critical data that needs to be updated immediately, like inventory levels or product details, they probably use event-driven invalidation. When the source data changes in the database, for example, an inventory update is committed, an event is triggered that explicitly tells the cache to invalidate or update the corresponding entry right away. They also rely on standard cache eviction policies like LRU, least recently used. When the cache is full, the oldest, least accessed items are automatically removed to make space for new ones.
Makes sense. Now, for distributed locking, which is a really deep and often debated topic in distributed systems, you mentioned Shiprocket likely uses the Redis red lock algorithm. Let's dig into that choice again. What's the thinking and the trade-offs involved?
This is a great point for discussing pragmatic engineering choices. Shiprocket appears to use the Redis red lock algorithm for many of its distributed locking needs across different services. The basic idea of red lock is to try and acquire a lock by setting a key with a random value in a TTL on multiple independent Redis master instances, say 3 out of 5. Only if the client successfully acquires the lock on a majority, the quorum of instances within a certain time limit, is the lock considered valid.
Why multiple instances? Why not just one?
The idea is to increase fault tolerance. If you rely on a single Redis instance and it crashes or has a network partition just after granting a lock, another client might be able to acquire the same lock from it upon restart, leading to a safety violation, two clients holding the same lock. Redlock tries to mitigate this by requiring a majority. It also includes a time to live TTL on the locks, typically short, 2 to 5 minutes, so if a client crashes while holding the lock, it eventually expires automatically, preventing permanent deadlocks. This is often implemented using libraries like Redison, configured to talk to multiple Redis nodes.
Okay, that's the mechanism. Now, this choice is interesting because while Redlock is popular and often chosen for its perceived simplicity and performance within an existing Redis ecosystem, it has also faced significant criticism, most famously from Martin Kleppmann, regarding its theoretical safety guarantees, especially under edge cases involving network partitions or precise clock synchronization assumptions. How does Shiprocket likely balance this?
That's the crux of the trade-off. For Shiprocket's scale and high-throughput requirements, Redlock provides a relatively lightweight, low-latency mechanism for mutual exclusion that works well most of the time for many efficiency-focused operations. The performance gain and ease of implementation within their Redis infrastructure likely outweigh the rare theoretical risks for certain use cases. It's often considered good enough and practically sufficient for their needs in many scenarios.
So pragmatism over theoretical purity for some cases.
Exactly. However, the key insight, as we discussed with the account service, is that for truly safety-critical financial operations where absolute correctness is non-negotiable, they explicitly fall back on the stronger, provable guarantees of database-level pessimistic locking within a single service boundary. They don't use Redlock for updating account balances. So it's a pragmatic, risk-assessed choice. Use Redlock where its benefits, performance, simplicity align and the risks are acceptable, but use stronger, albeit potentially slower, mechanisms like database locks for operations where correctness is paramount. They also employ techniques like lock striping for high-contention resources, like popular SKUs even when using Redis locks. Instead of one global lock key in Redis, they divide locks into n shards. For example, lock.resource.shard, where shard agils hash resource. This dramatically reduces contention for Redis locks, just like it does for database locks.
Okay, that's a very nuanced look at their locking strategy. Now let's talk about their event-driven architecture. It's important to clarify upfront, based on the system's behavior, that Kafka, or a similar message queue, is not used for the core synchronous order processing path. Its role seems more specific and decoupled, right?
That's a crucial distinction. Kafka, the popular distributed streaming platform, plays a significant role, but strictly for decoupling non-critical asynchronous processes. It's not on the main request-response path for creating an order or generating a label.
So what is it used for?
Several key things. One is operational notifications. For example, when the order service successfully processes an order or the label service generates a label, it might produce an event onto a Kafka topic, like for G, order shipped or label generated. A separate dedicated notification service consumes these events and handles the actual sending of transactional emails or SMS messages to the seller. Critically, if Kafka happens to be down temporarily, core shipping functionality, creating orders, generating labels, remains unaffected. Notifications might be delayed, but the main business flow continues.
Decouples notifications from core logic. Makes sense. What else?
Another major use case is the analytics data pipeline. They likely use change data capture CDC tools like Debezium to watch the production databases post-RESTful. Debezium captures row-level changes, inserts, updates, deletes as events, and streams them into Kafka topics. From Kafka, these raw change events can be consumed by a separate pipeline, maybe using Spark Streaming or Flink, that cleans, transforms, and loads the data into a data lake, like S3, or a data warehouse, like Redshift or Snowflake, for business intelligence, BI, reporting, and analytics. This keeps heavy analytical workloads completely isolated from the production transactional databases.
Right, feeding the data lake without impacting production performance.
Exactly. And thirdly, for audit trail. Critical operations across various services likely generate detailed audit events. For example, user logged in, order canceled, balance updated. These events are published to specific Kafka topics consumed by a central audit service. This service formats them and stores them in long-term immutable storage again. Think S3 with object lock enabled, maybe retaining logs for 7+ years to meet compliance requirements. This provides a secure, non-tamperable record of significant actions within the system.
And how do they handle concurrency and potential failures when processing these Kafka events?
For concurrency handling and event processing, they use standard Kafka best practices. Events related to a specific entity, like all events for seller or DBC, are often published with that ID as the Kafka partition key. This ensures that all events for a given seller are processed in order by a single consumer instance within a consumer group, maintaining consistency. Consumers are designed to be idempotent, meaning processing the same event multiple times, which can happen in distributed systems, doesn't cause incorrect side effects. For critical financial events piped through Kafka, like maybe for reconciliation, they would strive for exactly once semantics using Kafka's transactional capabilities or idempotent producers combined with idempotent consumers, ensuring each financial event is accounted for precisely once.
Yeah, okay. Lastly, within this data layer, there's the notification system itself. You mentioned a dedicated service consumes Kafka events. Is this notification capability something sellers interact with directly via API?
No, that's an important clarification. The notification delivery mechanism appears to be handled entirely internally by Shiprocket. There are no public API endpoints exposed for sellers to manage notification templates or delivery preferences.
It's purely for Shiprocket's own operational messages.
Exactly. The operational scope is strictly limited to transactional notifications triggered by system events. Things like your order has shipped, NDR detected for shipment X, your pickup is scheduled, or maybe low balance alert. There's no capability for sellers to use it for marketing messages or to highly customize the standard operational notifications. Internally, though, it follows FN-grade implementation principles. It likely includes features like delivery receipt tracking, knowing if an email was opened or bounced, automatic provider failover, example if SendGrid API fails, automatically retry sending via AWS SES, template versioning, and rigorous rate limiting per channel, email, SMS, and per provider to avoid being blacklisted. For concurrency control, it uses internal request queuing to handle bursts of notifications, adaptive concurrency limits per channel, and possibly distributed locks for ensuring critical notification sequences are sent in the correct order.
All right, let's dedicate some focused time now to really synthesize what makes this entire distributed system hum under load. Concurrency and thread safety. We've touched on specific techniques within individual services, but let's pull it all together for a deeper dive into the core principles Shiprocket employs across the board.
This is absolutely fundamental for any high-scale multi-service architecture. As we've seen, they strategically employ several database concurrency models. Optimistic concurrency control, OCC, is the dominant pattern, used for perhaps 80% of their business entities, orders, manifest returns, addresses. It relies on that version column check, where version advertise, during updates, detecting conflicts after they happen and requiring a retry. It's efficient when conflicts are relatively rare and is nicely supported by frameworks like Spring Data JPA's version.
Right, OCC for the common case, but when conflicts absolutely cannot be allowed or are expected to be frequent,
that's when they switch to pessimistic locking. This offers stronger upfront guarantees but can impact overall throughput. It's reserved for those truly safety-critical financial operations in the account service and perhaps for high-contention inventory updates. It uses explicit database row locks, select for update, acquired at the start of a transaction, preventing any other transaction from interfering until the lock is released. Implemented via JPA's lock mode type.pessimistic right, it guarantees consistency even under heavy contention.
and beneath both those application-level strategies sits PostgreSQL's own powerful engine.
Correct. They heavily leverage PostgreSQL's default multi-version concurrency control, MVCC. This allows concurrent transactions to work with different snapshots of the data, meaning readers don't block writers, and writers generally don't block readers. It provides snapshot isolation, which is crucial for consistent reads and allowing long-running analytics queries without impacting the performance of short transactional operations.
We also can't forget the carefully designed reserve capture pattern for financial operations, which seems purpose-built to handle concurrency safely in their specific prepaid model.
Indeed. That pattern, implemented using atomic database transactions within the account service but orchestrated across services, is a prime example of designing for concurrency at the business logic level to prevent race conditions in a distributed flow, ensuring financial integrity.
Okay, moving beyond the database, distributed locking becomes essential for coordinating actions across different service instances, or even different services. You explained Shiprocket primarily uses the Redis red lock algorithm for this. Let's revisit the nuances here.
Yes. For many of their distributed coordination needs, preventing duplicate label generation for the same shipment ID across multiple label service instances, ensuring only one NDR resolution action proceeds. Coordinate pickup scheduling, they employ the Redis red lock algorithm. As a reminder, this involves acquiring a lock from a quorum majority of independent Redis master nodes, using a random value as the lock token, and setting a TTL to prevent permanent deadlocks.
And the rationale again for choosing Redlock, acknowledging the known criticisms.
It boils down to pragmatism and fitness for purpose in their context. Redlock offers a relatively simple, low-latency, and high-performance distributed locking solution that integrates well within their existing extensive Redis infrastructure. For many of their use cases, it provides locking guarantees that are good enough and sufficient for their operational scale. The simplicity and performance benefits often outweigh the theoretical risks highlighted by critics like Kleppman, which often require specific failure modes, like precise clock drift combined with network partitions and process pauses, to manifest. However, the crucial point is their selective use. They understand the trade-offs. For operations where absolute mathematically provable safety is paramount, like core financial ledger updates, they consciously avoid Redlock and rely on the stronger guarantees of database-level pessimistic locking within a single service. It's a calculated decision based on risk assessment for each specific use case.
That distinction is key. And to further mitigate contention, even with Redis locks, they use lock striping.
Exactly. Lock striping applies just as well to Redis locks as database locks. For high-contention resources like popular SKUs or maybe frequently accessed sellers, instead of having all processes compete for a single Redis lock key, for example, lock.sku.123, they divide the resource into n logical shards. The example shard equals hasQ per 16, and use separate Redis keys for each shard, lock.sku shard part 5. This dramatically reduces contention on any single Redis lock key, improving overall throughput for concurrent operations.
Beyond explicit locking, what general thread safety patterns do they likely emphasize in their Java, presumably Spring Boot, code base to manage concurrency within each service instance?
Standard best practices are key here. Designing services to be primarily stateless is fundamental, meaning service instances don't hold client-specific state between requests, making them easily scalable and resilient to instance failures. Using immutable data structures wherever possible, especially for domain objects passed between threads or methods, is crucial. Immutable objects, once created, cannot be changed, which inherently eliminates entire classes of concurrency bugs. Using thread local storage is common for managing request-scoped context, like storing the X request ID trace identifier or security context for the duration of a single thread's execution without interfering with other threads. For shared mutable state, which should be minimized, patterns like copy on write might be used for things like configuration objects that change infrequently. Updates create a new copy rather than modifying the shared object in place. And of course, leveraging Java's built-in concurrent collections like concurrent hashmap or concurrent linked queue provides efficient and thread-safe ways to manage shared data structures when necessary.
Finally, none of this matters if the system falls over under real-world load. Load testing and performance must be a continuous and critical activity.
Absolutely crucial. You have to assume the system will be hammered. They undoubtedly perform rigorous load testing, likely simulating loads far exceeding normal traffic, maybe 5x or more, to specifically identify bottlenecks and ensure stability during peak events like major Indian festivals or sales days, big billion days, etc. They establish specific concurrency limits or target RPS requests per second for each critical service based on this testing, like we saw, maybe 1,000 RPS per shard for the order service, 500 RPS for the financially critical account service, 800 RPS for the label service, often limited by external carriers. Continuous monitoring and profiling in production identifies bottlenecks, and implementing adaptive throttling mechanisms allows services to gracefully degrade or slow down processing when upstream dependencies or their own resources are overloaded, preventing catastrophic system collapse during unexpected traffic surges.
That's a fantastic deep dive into the concurrency strategies holding this complex system together. Let's now take an equally deep dive into carrier API integration. This is absolutely fundamental to Shiprocket's core business. Without reliable carrier connections, nothing ships.
Indeed. This is arguably one of their most complex and critical areas. Shiprocket's carrier integration patterns are notably pragmatic and deeply customized to each carrier. They seem to favor direct API integration. This means they build specific integration code to talk directly to the native APIs of carriers like FedEx, Delivery, Blue Dart, Ecom Express, etc., rather than trying to build a single generic abstraction layer that attempts to hide the differences between carriers.
Interesting. So they don't have a unified carrier adapter interface.
It appears not extensively for the core operations. While that approach might offer some code reuse, it often leads to a least common denominator implementation that can't take advantage of unique carrier features or handle specific carrier errors effectively. By integrating directly, they sacrifice some code reuse but gain precise, carrier-specific handling, which is critical for reliability, accessing advanced features like specific service types, and managing the nuances of each carrier's API. They use official SDKs, like a FedEx Java SDK. When provided and reliable, build custom REST clients using libraries like Feign or Retrofit, for many others, handle XML-based APIs for older systems like Blue Dart sometimes requires, and integrate via webhooks for incoming tracking updates when carriers support that. The trade-off is higher initial implementation and ongoing maintenance cost per carrier, but it provides unparalleled control and reliability, which is essential for a core logistics platform.
Okay, that direct integration approach makes sense for maximizing capability. Can you give us some specific examples of these carrier-specific implementation details? How might they differ?
Certainly. For a global player like FedEx, the integration likely involves using OAuth 2.0 for authentication and interacting with distinct APIs like their Ship API for creating shipments, Rate API for getting price quotes, and Track API. Error handling needs to be robust. Knowing how to handle FedEx's specific 429 rate limit responses, likely requiring exponential backoff, and implementing a circuit breaker for intermittent 5x server errors from FedEx's side. Rate limiting is crucial, adhering strictly to FedEx's documented limits, for example, maybe 50 requests per minute, using a precise token bucket algorithm and potentially request queuing during bursts.
Okay, and for a major Indian domestic player like Delivery, how might that differ?
For delivery, authentication might use a simpler API key with request signing. They have their own specific APIs for creating shipments, generating manifests, with that minimum shipment count rule, and tracking. Delivery's error handling might involve different custom error codes that need specific mapping. They might return 503 service unavailable errors requiring a circuit breaker. Their API might also support partial failures in bulk requests, which needs careful handling. Their rate limits might be different, Surgy maybe 30 requests per minute, again requiring a dedicated token bucket and possibly adaptive rate control based on observing Delivery's API responsiveness.
And you mentioned Blue Dart using XML.
Yes, Blue Dart, another major Indian carrier, historically has had XML-based APIs for some functions. Integrating with them requires specific libraries for XML deserialization and handling their particular request signing mechanisms. They might also handle partial failures differently and often provide tracking updates via webhook pushes rather than polling APIs. This just illustrates the diversity Shiprocket has to manage.
Wow, the heterogeneity is incredible. Across all these diverse integrations, error handling and resilience must be absolutely paramount to keep shipments flowing.
It's nonstop firefighting and prevention. They need detailed carrier-specific error code mapping, translating hundreds of potentially cryptic error messages from dozens of carriers into standardized internal error categories that their system and support teams can understand and act upon. They implement custom retry policies with exponential backoff, carefully configured for each carrier, deciding which errors are transient and worth retrying, like temporary network glitches, and which are permanent, like invalid PIN code, and should fail immediately. As we discussed, circuit breakers, likely using Resilience 4J or similar with adaptive thresholds tuned per carrier, are essential to isolate failing carrier APIs and prevent cascading failures, and robust fallback mechanisms are likely in place for critical operations like label generation. If the primary carrier API fails, can the system automatically try a secondary pre-approved carrier for that route?
And managing those different rate limit management policies for dozens of carriers simultaneously must be a constant balancing act.
It's incredibly complex. They absolutely need a per-carrier token bucket algorithm implementation to precisely track and enforce the specific rate limits for each one. This is often complemented by adaptive rate control, where the system monitors the real-time latency and error rates from each carrier's API and dynamically adjusts the outgoing request rate, throttling down if the carrier seems overloaded even before hitting the hard rate limit. They use request queuing internally to buffer outgoing requests during peak loads, smoothing out bursts directed at carrier APIs. And wherever possible, they utilize batch processing if a carrier API supports it, example, tracking multiple shipments in one call, as this significantly reduces the number of API calls needed.
That carrier integration piece is fascinatingly complex. Let's now tackle another area of major complexity: multi-platform synchronization. This is where Shiprocket navigates the equally challenging task of integrating deeply with diverse external e-commerce platforms like Shopify, WooCommerce, Amazon Seller Central, Flipkart, Magento, and others, keeping orders and inventory aligned.
Yes, this is the other side of the integration coin, equally critical and complex. Their e-commerce platform integration approach is necessarily hybrid and adaptive because just like carriers, these platforms have vastly different capabilities and APIs. They prioritize webhook registration whenever a platform supports it reliably. For platforms like Shopify and WooCommerce, this allows Shiprocket to receive near real-time notifications. For example, new order created, product updated, directly from the platform, enabling very fast synchronization.
But not all platforms offer good webhooks, right?
Exactly. For platforms with limited or no reliable webhook support, particularly marketplaces like Amazon Seller Central or Flipkart Seller Hub, Shiprocket has to rely on a robust polling mechanism. This involves scheduled jobs that periodically connect to the platform's API using secure OAuth 2.0 flows for authentication and actively query for changes. Give me all orders since timestamp X. They also need diligent API quota management for each platform, carefully tracking their usage against published limits and implementing throttling or backoff to avoid getting blocked. This adaptive approach, mixing webhooks and polling, increases implementation complexity, but is essential for achieving reliable synchronization across such a diverse ecosystem.
Okay, now let's revisit inventory synchronization, specifically in this multi-platform context. This is arguably one of the hardest problems in e-commerce. You mentioned Shiprocket likely uses a vector clock algorithm here for maximum consistency.
Yeah.
Can you elaborate on the implementation and trade-offs again?
Certainly. Maintaining accurate inventory when a seller sells the same product across multiple channels, for example, their own Shopify store and Amazon, is incredibly prone to race conditions and overselling. To combat this with the highest degree of accuracy, Shiprocket's platform sync service likely uses a vector clock algorithm during the synchronization process. As we discussed, the implementation involves, for each SKU, maintaining not just a quantity but a vector clock, a map of platform logical timestamp. When an inventory update event comes from, say, Shopify, Shiprocket increments Shopify's timestamp in the vector clock for that SKU. When comparing an incoming update's vector clock with the currently stored one, Shiprocket can determine the precise causal relationship. Did update A happen strictly before update B? Did B happen before A? Or did they happen concurrently without knowledge of each other?
And why choose this complex method over simple timestamps?
That's the crucial choice and trade-offs discussion. Vector clocks are chosen here because they provide precise conflict detection and enable sophisticated resolution logic based on causality. They can prevent lost updates, where a slightly later timestamp from one platform might incorrectly overwrite an update from another platform that happened concurrently but wasn't causally related. This is vital for preventing overselling, the nightmare scenario for any e-commerce seller. The acknowledged trade-off is complexity. Vector clocks add storage overhead. The vector grows with the number of platforms, and comparisons are computationally slightly more expensive than simple timestamp comparisons. Simpler last write wins, LWW, based on wall clock timestamps, is easier to implement, but carries a higher risk of data loss or inconsistency due to clock skew between systems or overlooking causal dependencies. For critical function like multi-channel inventory sync, the stronger consistency guarantees offered by vector clocks often justify the added complexity.
Okay, so vector clocks provide the mechanism for detecting conflicts. How are conflicts actually resolved? What are the conflict resolution policies?
Once a conflict is detected, for example, two concurrent updates with no clear causal order, Shiprocket needs predefined policies. Common approaches include last write wins, but using the most precise timestamp available, maybe within the vector clock context, potentially configurable platform priority. For example, a seller might designate their Shopify store as the ultimate source of truth, overriding concurrent updates from Amazon, flagging the conflict for manual resolution by the seller for critical discrepancies, or simply applying a default rule and logging the conflict meticulously for auditing. The goal is usually to prioritize operational simplicity and consistency, resolving most conflicts automatically while providing visibility for exceptions. Delta synchronization is also key for efficiency here. Instead of constantly pulling full inventory lists, the sync service focuses on processing only the changes reported by the platforms, often using platform-specific change tracking APIs and then batching these Delta updates for efficient processing.
And finally, for concurrency and multi-platform sync, how does Shiprocket manage the locking and parallelism needed here?
It uses a combination of techniques. Distributed locking, Redis redlock, is likely employed during the critical step of applying a resolved inventory update to Shiprocket's internal cache, especially for high-contention SKUs, to prevent race conditions from concurrent sync processes working on the same item. Adaptive concurrency control is used to manage the rate of polling or processing updates based on platform API limits. The conflict detection relies heavily on those vector clocks, and all operations that modify state, like updating the cached inventory level, must be designed to be idempotent so that accidentally processing the same update event twice doesn't corrupt the data.
We have covered an absolutely tremendous amount of technical ground today, exploring the architecture and intricate workings of Shiprocket. Before we wrap up, though, it's really vital to also understand what Shiprocket doesn't do. This section on critical architectural boundaries is crucial for clarifying their precise scope and appreciating their strategic focus. It's about the power of saying no.
Absolutely. Understanding the boundaries is just as important as understanding the features. It shows strategic discipline. Firstly, and perhaps most importantly, Shiprocket never handles end customer payment processing. When you buy something from a seller using Shiprocket, Shiprocket is not involved in charging your credit card or processing your UPI payment. That's entirely handled by the seller's e-commerce platform and their chosen payment gateway.
Right, big distinction.
However, Shiprocket does manage the seller-to-carrier payment processing. That relationship, funded by the seller's prepaid credit balance and using that reserve capture pattern, is core to their model. They pay the carriers on behalf of the seller using the collected credits.
Okay. And critically, regarding inventory.
Shiprocket only syncs inventory levels for informational and operational purposes, like serviceability checks or basic validation. It does not act as the inventory management source of truth system and does not perform transactional inventory reservations. The seller's e-commerce platform, Shopify, Magento, etc., remains the true authoritative source of stock information.
Got it. What about user authentication?
Shiprocket does not handle end-user authentication. It doesn't manage customer logins or accounts for the seller's stores. Its auth service is purely for the seller's system machine-to-machine authentication. Similarly, while Shiprocket syncs product data, it's not the product catalog management primary system. Sellers manage their products primarily in their e-commerce platform.
And notifications.
Shiprocket only sends operational notifications related to the shipping process, shipped, delivered, NDR, pickup. It does not offer capabilities for sending marketing notifications. And while it manages the return logistics, it does not handle automatic refunds. Those require separate processing by the seller after Shiprocket confirms the return is complete.
Finally, that interesting point about carrier integration.
Yes, Shiprocket notably does not use a generic carrier API abstraction layer that tries to hide the differences between carriers. Instead, it pursues direct API integration with each carrier's specific native API, allowing for deeper integration and better handling of carrier-specific nuances, despite the higher development cost. However, one area that is fully automated is receiving and processing automated carrier status updates. Scan events like picked up, in transit, out for delivery, delivered flow automatically from carriers into Shiprocket without human intervention.
That clear focus is really powerful. It prevents scope creep and allows them to excel at their core logistics competency. So let's try and recap this incredible journey. We've taken a really deep dive into Shiprocket's complex architecture today. We started at API Gateway, exploring its role in security, rate limiting, and observability. We then journeyed through each core service order, account label inventory sync, courier selection, returns, NDR, manifest, pickups, platform sync, channel management, addresses, products, and auth. We've seen how they handle everything from robust JWT authentication and sophisticated database concurrency control using both optimistic and pessimistic locking to advanced distributed locking with Redis Redlock and its trade-offs. We explored how they tackle challenging multi-platform inventory synchronization using vector clocks for causal consistency, and how that absolutely critical reserve capture pattern ensures financial integrity in their prepaid model.
It's a fascinating blend of standard best practices and solutions tailored very specifically to the Indian logistics market and their business model.
Absolutely. This architecture really feels like a testament to pragmatic engineering. It's solving real-world, often messy logistics problems in a complex market like India, with a blend of robust, FAANG-grade best practices where appropriate, but also highly tailored, sometimes simpler solutions where pragmatism dictates. This whole deep dive aimed to be a comprehensive source of truth, making these complex engineering choices clear.
And I think in a world that sometimes pushes for theoretical perfection or the latest shiny object in technology, Shiprocket serves as a great case study. It shows us that true mastery often lies in that pragmatic alignment with reality. It's about deeply understanding the problem domain, knowing what to build, knowing what not to build, and making those difficult but necessary trade-offs to achieve reliability and scale where it truly matters for their specific business and customers.
That reminds me of that great quote often attributed to Antoine de Saint-Exupéry. Perfection is achieved, not when there is nothing more to add, but when there is nothing left to take away. Shiprocket's focus seems to embody that.
That's a perfect way to put it. Focus and pragmatic execution.
So here's a final thought for you, our listener, to mull over. What aspects of your own work, the systems you build or manage, could benefit from such a focused, pragmatic approach? Where could you perhaps simplify, clarify boundaries, prioritize more effectively, and make those hard-won trade-offs not just for features, but for greater reliability, scalability, and ultimately, impact? We really hope this deep dive has given you some incredible insights into the complexities and solutions involved in building resilient, high-scale distributed systems, especially in the challenging world of logistics. Keep exploring, keep learning, and please join us next time on The Deep Dive.